Okay, now that you've had a chance to hopefully explore the Whipple Mountains on your own a little bit, now we're going to dive in and use this interesting case study to define what a metamorphic core complex is and the structures that compose it. So, to define a core complex, these are features of major continental extension that exhibit the following key characteristics. They represent domed or antiformal mountain ranges. They have upper plate rocks that are highly distended by closely spaced brittle normal faults. They have flanking low angle normal faults of subregional to regional extent. These are referred to as detachments. And the lower plate core of the complex consists of high strain rocks that progress from low to high metamorphic grade with increasing structural depth. This example image is for the Rincon Catalina core complex in southern Arizona, but we'll look at each of these key characteristics as exposed in the Whipples today. So as we noted in the last video segment, core complexes are domal mountain ranges. The figure on the right includes a cross-section through the Whipples from southwest to northeast and crosses the Whipple Detachment Fault itself. And you can see that the detachment is a curved structure that dips west in the west and east in the east. And the highest topographic point in the mountain range is in the center of it. The upper plate of the Whipples consists of these dark basaltic rocks, and it's quite distended or pulled apart by high angle normal faults and intervening fault blocks. Here we're going to look at a photo taken looking toward the northeast. And you can see all of these normal fault bounded linear ridge lines that repeat this basaltic unit over and over again and extending into the distance. The primary structure in the Whipples, though, is of course the flanking low angle normal fault, the Whipple Detachment Fault itself, that, as we talked about in the Google Earth tour, generally bounds the mountain range on all sides and is very shallowly dipping. Here's a view of the Detachment Fault looking toward the northwest. It's this sharp contact in the foreground and the background. Zooming in on this nice clippa, we see that this contact, the detachment, is nearly knife sharp, and it separates tertiary volcanics, mostly basalt lava flows, from footwall granitoids that here I've labeled mylonites, which you may recall is a term for high strain, ductily deformed rocks that we'll discuss in more detail shortly. And it should be clear right away that this cannot be an intrusive contact because it is just too planar and there's no evidence for injection of plutonic rock. The granite, for example, shows no evidence for intruding into the basalts above them. And in fact, the sharpness of this contact really misled geologists for a long time. It was originally mapped, in fact, as an unconformity over and over again through the 50s and into the early 80s, just because of how planar, sharp, and low angle the contact is. But what really started to convince people in the 80s that this was in fact a fault was the remarkable evidence for deformation and a very systematic sequence of deformation that we now know characterizes core complexes actually all over the world. I'm showing this sequence sort of schematically here, and this is meant to represent the different deformation features that we see as we step structurally downward from the detachment fault itself into the interior of the metamorphic core. We see at the top a zone of very discrete faulting decorated with hydrothermal alteration that grades downward into a zone of brecciation, cataclasis, and seismic slip that grades down further into shear zones that are both brittle and ductile and that show evidence for green schist facies metamorphism. And then finally, it grades down even further into a zone of widely distributed and penetrative ductile deformation, forming mylonites that show evidence for amphibolite facies deformation. So in the simplest senses, what the core complex is preserving is actually the brittle ductile transition of the continental middle crust. It's a snapshot, so to speak, of the boundary between the seismogenic crust, where everything is mostly brittle and discrete, and the flowing, sort of squishy middle and lower crust, where temperatures are higher and everything is ductile. So let's look at some of the geological features that constrain this. Here's another view of the detachment fault itself, now in the south side of the range. It's extremely discrete. It even defines a sort of prominent ledge that you could see from a great distance. In some places, you can stand on top of this ledge-like detachment exposure. It's been colloquially named here the dance floor detachment because of how planar and polished it looks. There's even some nice prickly pear cacti, also called teddy bear cholla, there that one could dance with, although they're not as friendly as they look. They're definitely pretty spiky. And the detachment itself shows evidence for also having concentrated hydrothermal fluids when it was active. So there's quite a bit of ore mineralization along it, copper, some bits of gold. It was in fact prospected by a famous Wild West Texas lawman, some of you may have heard of, known as Wyatt Earp. Lots of Hollywood movies made about him. He called this prospect I'm showing on the left his lucky day prospect, although sadly he did not find enough gold for it to be economical, so it really wasn't his lucky day. He ended up retiring nearby in the town of Parker, Arizona, and eventually gave up on Whipple gold digging. And then as we move structurally downward, immediately beneath the detachment, we start to see these distinct zones of brecciation and cataclasis. The detachment itself is commonly defined by a silicified microbreccia that forms those resistant lenses like we saw for the dance floor detachment. And then below them are these highly brecciated rocks, again, quite altered by hydrothermal and ore-bearing fluids. Here's an example of a chlorite-rich cataclastic zone, suggesting that some of these brittle fault rocks are starting to approach the green schist facies conditions where chlorite is a stable mineral phase. Another example of the high-strain brittle fault rocks preserved here, just a breccia grading into a cataclysite and ultimately an ultracataclysite. There's also preservation of something called pseudotacolites, which are one of the few structures that tell us about ancient earthquake slip. These represent fault slip surfaces where the slip rate was so fast the rock actually locally melted due to frictional heating. So these are essentially paleo earthquakes, and they're quite abundant also beneath the Whipple detachment, hinting that this was a seismically active structure near the base of the seismogenic zone. So we progress deeper into the footwall, we start to encounter these structures that have both a brittle and ductile character. So this photo on the left, for example, shows a brittle, discrete slip surface near the green arrow, but that structure soles into the quartz band in the middle of the image and forms there a ductile shear band with no discrete slip. And that feature is sort of mimicked or repeated on the right of the image as well. Finally, as we go even deeper into the footwall, we enter into this higher temperature region of distributed ductile deformation and planar stacks of high strain myelinites. The green lines are highlighting the myelinitic foliation dipping toward the left in the west, left, which is west. Looking more closely in the right image, we see that these myelinites form augen gneisses, which are common under amphibolite facies conditions. So now we recognize that these myelinites are forming under higher temperatures. This image shows these big feldspar porphyroclasts, the augen, that have nice wings and tails that are stretched out in the foliation orientation, and they're surrounded by white planar streaks of quartz, biotite, and in some cases tabular-oriented amphibole. So that's a summary of the key geologic ingredients that form metamorphic core complexes. Hopefully I've convinced you of their origin as essentially tectonic or deformational features. But one of the things I haven't discussed is how we actually know that these are normal faults in particular, as opposed to thrust faults or strike-slip faults, for example. All we see at first glance is this stark contact with lots of deformation fabrics, and also the fault itself is actually curved into an antiformal shape, so it's not particularly uniformly dipping. So even if we were able to recognize offset features or particular shear sense indicators, in some places the shear sense would look reverse sense, and other places it would look normal sense. So it turns out the primary clue is actually what's juxtaposed on either side of the Whipple detachment. The tertiary volcanic rocks in the hanging wall essentially form at Earth's surface. They're not even intrusive rocks, they're extrusive basaltic lava flows. These footwall mylonites, on the other hand, are 300 plus degrees, so several kilometers of crustal section is actually conspicuously missing between the surface volcanics and the mid-crustal mylonites. Let's just do a quick thought experiment to figure out how this helps us recognize this as a normal fault. So here I have a crustal column cut by a moderately shallow fault, going from the surface down to amphibolite facies. Now let's offset it in a thrust sense, as in the diagram on the left, and then let's pretend that we erode the surface down a little bit, as shown in the diagram on the right. And what we should find is that the thrust fault actually duplicates section and is placing hotter rocks from the amphibolite facies on top of colder rocks beneath them. So this in fact does the exact opposite of what we see showing up along the Whipple detachment. Now, if we consider the normal faulting case, we displace the hanging wall downward, then we erode a bit off the surface, and now we find a situation that nicely matches the Whipple detachment case, where the normal fault effectively removes section, this is called excision, and it places colder rocks from the surface on top of much hotter rocks from the green schists and warmer middle crust. So this relationship is how, despite that we don't have a lot of displaced markers since the fault is so large, and despite that its orientation varies a lot over its entire fault area, this is how we're still able to recognize that the Whipple detachment represents a very large-scale extensional structure that effectively excises a several kilometer thick section of the brittle upper crust. And this distinction between normal and thrust faults and how they duplicate section in the thrust case versus remove it or excise it in the normal fault case is a key one that's actually used all over the world to recognize these kinds of structures, especially in dominantly ductile rock sequences that exhibit many phases of overprinting deformation. So thanks for your attention. The next segment we'll talk about the mechanics of core complex development.